Hello, good afternoon. Can you hear me? Okay, so if you can hear me, can you please type a yes and let me know we're okay?
Yes.
Okay, great. Thank you, Dr. Chen. And thank you, Brandon. Okay, let me see our chat. Okay, great. Yeah, thank you, Amy. All right, this is great. Well, hi, everyone. This is our last lesson of this USACO using MIT App Inventor. Today, like always, this is not the last lesson. This is actually a start lesson for our next step. So today we will invite Kevin Meng. He is a sophomore. He's a rising sophomore of MIT in the EECS department. He was a USACO competitor. He was a winner of International Science and Engineering Fair. He was the first grand prize winner of Hack MIT, which is a programming competition. He is I think he is a exemplary student of ours. So which carries, which represents something like some education goals in our dream, right? So yeah, let's invite Kevin. And so Kevin, are you there already?
Yeah, hey everyone, glad to be here. And yeah, so I think today what we're going to do is I will just talk a little bit about how you can continue with your competition path once this class ends, because as we've been talking about, this is only the beginning. There is so much else to do. And today, I think I'll just outline a couple of things that you should keep in mind so that you can actually compete in USACO when the competition season starts in December. And we're currently at the end of July, at the beginning of August. So you have plenty of time. I believe that if you've been able to solve all of the problems in this class fairly reasonably well, you will be able to make silver by the December contest, guaranteed, as long as you've really grasped the concepts well. So let's go ahead and dive right in. We'll just talk about some of the things that you should keep in mind. Now, just like a quick note, feel free to take notes because I don't have any slides for you all today. I will be sending out links as I talk about them, so you can copy and paste them into your text editors or whatever, but no slides today. So make sure that you remember everything that's said. Anyways, so let's get started. The first thing that you should keep in mind is that you need to learn an actual programming language to compete in USACO. So this can take the form of many different things. You can look at Python, you can look at Java, you can look at C++. You can even look at some very obscure and rarely used languages like C. But this is pretty much the last one that they support. They took out all the ones like Pascal. No one uses them anymore. So yeah, the first step is going to be learning a language. So if I share my screen, I can share a couple of resources that you can use to do this. One of them is going to be Code Academy, the Code Academy. And you probably want to look at one of the following languages, either Python, C++, or Java. These are the three most popular ones. And if you ask me about one of them, I recommend C++, simply because once you get the syntax down under your fingers, it's very fast, much faster than Python, and even faster than much faster than Java, and even faster than Python. And it has a lot of the standard template algorithms that are already implemented in its library, so you don't have to re-implement them. So that's very convenient. There are a lot of features, for example, like binary search, that you do not have to code yourself frequently because in most cases, it'll be implemented in C++ already. So this is probably the first step. So what I'd recommend is, because you already know how to code in MIT App Inventor, and a lot of the functions are actually exactly the same, I'd recommend looking through this course, just going through this course It's a very basic course. It'll only teach you the fundamentals, but you should be able to blaze through it in probably a day or so, or even less. Because if you look at the syllabus, basically what they talk about is your hello world is quite simple, but they talk about variables, conditionals, loops, vectors, functions, classes and objects, references and pointers. These are actually all things that you have quite a deep understanding about through MIT App Inventor, even though it might not seem like you know how to program because you've just been dragging blocks everywhere. What you should realize is you've actually learned to code without having to deal with the annoying syntax. And this is the time when you can actually use this ability to rationalize and think about problems computationally, and then apply an actual programming language to learn the syntax. It's not that hard anymore because you've sort of separated, you've stratified these two different parts of learning a language or learning coding, and it's going to be far easier for you. Um, so yeah, in fact, a lot of these topics should look very familiar to you from MIT App Inventor. Variables, creating local and global variables, conditionals and logic, if statements, those kinds of things, loops, while loops, for loops, termination conditions. These are all things that that are in fact critical to coding in C++, but you already know them, which is amazing, and that's wonderful. And the key part is you didn't have to slug through all of the annoying syntax to actually grasp all of these concepts, which I think is really cool. Anyways, you should be able to blaze through this course very, very quickly. If not in a few days, then maybe a week if you're going a little bit slower. But after you complete this, and I'll just send this in the Zoom chat. After you complete this course, all you have to do is practice. You need to do a lot of practice. There are a couple of resources that I'd recommend for this. The first of which is train.usaco.org. Finish the first couple of pages. Just get as far as you can go with your current algorithms knowledge. At the very beginning, it is very basic concepts, but once you get to the second page, it'll get considerably more difficult. So just see how far you can go, and you can just test it out. Another resource that you've probably, I don't know if you've heard of, but this was something that was released after I stopped doing USACO. And it looks very helpful. It's called USACO Guide, and I'll send this link as well. But this is basically a guide where they've compiled all of the different topics that usually show up on contests, and they put them in these problem sets where you can go to sections for your division. We'd probably be looking at bronze, and these are all of the different topics. And if you click on any one of these topics, they have a really large quantity of problems that you can do. And I think this is definitely going to be the most important part to your success, which is, can you do enough problems to cover all of your bases so that when contest day comes, you will sort of recognize a lot of the patterns that emerge in a lot of these contest problems. And so then you can solve them. So definitely do a lot of practice. That's going to be the big thing. And keep in mind that if in, for example, 1 to 2 months, you've done pretty much all of these problems and you feel like you have a very good grasp of bronze and it's no longer a challenge for you to solve them. And basically how I would gauge this is, if you look at a problem and you know how to do it already, it's too easy for you. So once you get to that point, initially you won't feel like that. Initially, you will look at these problems and you'll be like, oh, this is kind of hard. How do I solve it? And you might think about it for maybe 15, 30 minutes, maybe even an hour. And then you sort of figured out what you need to do, and then you code it up using another 15, 20 minutes. That's basically when you're not familiar enough with the entire setup. So at that point, just keep doing bronze problems until you're comfortable with bronze problems. And this isn't so hard because bronze problems are all pretty straightforward. So you should be able to reach the point of being able to see a problem and instantly recognizing the solution very quickly. But the point of this discussion is, once you get to that point, don't just stay on bronze. You can actually just keep going, because getting to silver is not the end goal. You want to eventually make plat. So then if you feel like bronze problems are getting to that point where they're too easy for you, feel free to learn more algorithms and start doing silver problems. I'm sure that a lot of you will hit that point if you found the problems that were discussed in this class at least tractable. you do a few more problems, they'll become easy to you. And when they become easy, you need new challenges. So move up to silver. The way that you can do that, of course, this website is really great. I wish it existed when I was here. But if you just go to the next division, silver, they have a whole lot of different more topics. So silver is considerably more difficult than bronze, and they will have a lot of different algorithms that are a little bit more abstract and a little bit hard to wrap your head around when you're younger. But still, if you're interested, why the heck not? So of course, this guide has not only the problems, but they also have topic introductions. So there's this thing called a prefix sum that's often very helpful. And if you just click on it, there is an entire lecture. These are basically lecture notes for what prefix sums are and why they're useful. They support range queries very quickly, is the TLDR. But they have a very nicely written explanation for all of these things. And it's just very, very helpful for you to get your bearings on what types of problems are going to show up. And then, once you understand what is going on in this concept area, they have a whole lot of problems for you to just do. And this is going to be really, really helpful. Doing problems is for sure the most important thing that you should be doing. So yeah, it's just a really, really great resource. Like, these are all just lecture notes that they're going to that they've compiled for us, and it's really great. So definitely take advantage of this website. And of course, if you feel like before the competition season starts in December that you're already super good with bronze, then go ahead and move up. All of this can be self-studied, and all the power to you. All right, cool. So that is pretty much it. There is only one thing that I haven't talked about very, very carefully, which is the train.usaco.org training gateway. This is also a really good resource, and you should take advantage of it. Basically, you will start at chapter 1, and I think all of chapter 1 is pretty appropriate for is going to be pretty appropriate for bronze. So of course, like sections 1.1 and 1.2 are completely irrelevant because you already know. But sections 1.3 through 1.6 are quite useful. So the first one is complete search, which is simply bashing, which is trying all the possible answers and finding the best one or finding the correct one. There's greedy crafting solutions. So this is thinking about designing algorithms that sort of take shortcuts that turn out to be globally optimal. Or you might talk about search techniques, which is I'm assuming that they have things on depth first search, breadth first search. So when you get to 1.5 and 1.6, you start to tread into silver territory. So don't worry too much if some of the concepts are a little bit vague, but definitely get through 1.4. And if you're curious, keep going to 1.5 and 1.6. So this is all definitely really useful too. And especially because this is USACO created, a lot of them are quite useful for contest preparation. And their sort of write-ups are actually quite useful. So they have this thing called complete search. And this is actually a really, really good explanation of what complete search is. So yeah. Anyways, to recap, there are all of these resources that exist. Basically, your plan should be to, number one, do learn a language. You can't do USACO with MIT App Inventor, but the really nice thing is that because you know MIT App Inventor, picking up a full language will be very, very easy. So, so number one, learn C++. If you don't want to learn C++, that's okay. I wouldn't recommend it. I would still recommend learning CPP. You can also use Java. They do give double the amount of time to Java programs because Java is approximately twice as slow as C++. But when you go around, you will realize that pretty much everyone uses C++ as the gold standard, and often runtime limits will be measured against the C++ programs. So it's just a safer bet. If you don't have any major preference beforehand, learn C++. Python is great for other things, not competitive programming, because Python is about 10 times as slow as C++, if I remember correctly. Maybe not 10 times, but maybe at least four times. So twice as slow as Java. So yeah, number one, learn the language. This is going to be really easy for you if you have a solid grasp on MIT App Inventor. So once you learn the language, go to USACO Guide, go to the bronze section, and literally just go through all of these things and do all of the problems one by one. This should take not a lot of time, depending on how hard you work, of course. Like if you solve maybe 5 problems a day, you'll get through this entire set of problems by the time the December contest rolls around. Of course, you don't have to go that hard. That's pretty intense doing 5 problems a day. So just pick and choose. Also, don't really settle for doing things that you're already comfortable with. Really nail down on your weaknesses. If there's any concept where you're like, oh, I really hope this doesn't show up on the test, really emphasize that, because chances are if it's hard for you, it's hard for other people, and the organizers know that, so they will exploit that and they will put that stuff on the test just to see who's good and who's not. So yeah, learn a language, do a lot of practice. If you feel like you've gone to the point where bronze problems are really easy, you can think of the solution just like immediately when you look at a problem, then move on to silver. All right, cool. Does anyone have any questions before we move on? So this is sort of like the general, what do I do to compete in USACO? And in the latter half of this class, we're going to just do a problem and give some of you an idea of what it's like to program in C++, to program in maybe some other language and solve a problem that we haven't solved from USACO yet. And we're going to be solving it together. We will discuss the pseudocode, and then I'll code it up in C++, but I'll explain at every moment what I'm doing so that you can draw parallels to MIT App Inventor. So there's a question: how many problems should we do before we feel comfortable to compete in USACO Bronze? I mean, obviously it varies by person. You guys already have a really strong start because you've done 15 problems, and I'm assuming that you guys understood them pretty well. So that's already a huge start. Honestly, at this point, you may be able to look at just some arbitrary USACO Bronze problem and instantly be able to understand what's going on. So that's one thing. I would say that, a rule of thumb is to solve as many problems as you can, because you can never be too prepared for these kinds of things. Especially in a competition environment, you will forget things, you will overlook things, and the only way to overcome that is to be good, is to do more problems. Luckily, in bronze, there aren't many different things that could show up. Usually a good bet in bronze, if you see a problem that asks you to optimize or to count, basically combinatorics, either combinatorial optimization or just counting things, which is just combinatorics, just try all of the possible situations. And usually it'll work because it's bronze and the time constraints are very lax. So in general, that's like a good bet for bronze. You probably cannot fail by just trying to bash everything. So I don't have a good answer to this, but you should be doing problems from every single section. You cannot leave out anything, because then you will have a big knowledge gap. And in each section, you should do, let's say, at least 5 problems. And the 5 problems is not a hard number. It is just that I feel like at 5 problems, if you're able to solve 5 problems really easily, then you will be able to look at any problem in that section and just instantly understand what you need to do. And maybe if you reach 5 problems and you still feel really shaky, if you're doing your 6th problem and you're really confused, you don't know what to do, and it takes you like an hour to figure it out, then keep doing problems until you feel comfortable. So it's not about a number, it's about how good you feel about doing these problems. Yeah. And one thing that I haven't mentioned before I continue is that the environment in which you code is going to be a little bit strange to set up. So if you code in C++, you're going to need to figure out how to install a C++ compiler on your computer, how to set up your IDE. If you want to use Java, then you're going to have to install the JRE, the Java runtime environment. If you want to use Python, you're going to have to install Python. And so all of these things are really annoying. But there's a way that you can avoid this. There's this website called repl.it. You may have heard of it before. But basically, I can log in with my account. You can sign up with Google. Let's sign in with Google. And basically, if I create a new REPL, if you just hit create new REPL, name new REPL USACO problems, and you can select a language, C++. You can create a REPL. And basically what happens is they've installed all the compilers that you need on here. They've installed everything. All you need to do is code. So for example, if I include, I don't know if they don't have the entire one. Okay, so if we include IOStream, we set this to the standard namespace. We create a new function called main, and we just type out hello world. If I hit command enter, it'll compile it and it'll type hello world. So this is one way to do it using REPL so that you don't have to install anything on your computer. I personally like doing things on my computer because then you have benefits such as debuggers. One thing that you want to keep in mind though is that REPL also has a debugger, and so the resistance or the friction or the effort that you have to put in to actually install this kind of stuff on your computer is pretty insane. If you're on Mac, it's a little bit easier. Just because Mac is nicer, they've sort of packaged everything together. Mac actually comes with the compiler for C++, so you don't have to install that. You simply have to configure the debugger with VS Code or some IDE, and then you're set. But on Windows, I remember I had a huge amount of trouble because you have to install like something like MinGW or Cygwin, and that is a pain. So if you're just starting out, I would say that for now, when you're learning USACO, use REPL.it or Replit. I think that's what they call it, because it's just so much more convenient. You get to do the exact same thing just without the hassle of setting everything up. And it looks like they've also, added a debugger, which is really, really cool. And that's really powerful. Debuggers are really hard to set up locally. But anyways, this is what I would recommend for now. Let's use REPL. And today, I guess when coding, I will use REPL as well to just show you how to use REPL and why it's so great. Cool. And let me send this link in the chat so that you can keep it in mind. Or in fact, I will just compile all of these things into a document. So let's create a text edit document. Let's create a new one. And let's just list all the resources. So what are the things that I've listed? So Code Academy is one of them. Replit is one of them. Code Academy to learn. Okay, let me just type this out. One, learn language. So we can say C++, Java, Python. My preference is in that order, so I would not recommend Python for USACO. First is learn language. Number two is do a lot of practice. So we have two websites for that. We have train.usaco.org. And we also have usaco.guide. And then finally, three, or actually this should be number 3 and this should be number 2, which is set up programming environment. And you should be using Replit. Do not try to install something on your computer at the very beginning because you're going to spend a lot of time on it. It's probably not going to work and it'll feel really bad and that'll be discouraging. So instead just use Replit, and I'll show you guys how to use Replit today when we solve a problem. Cool. All right, so I think that's pretty much all of the in theory talk that I had. Does anyone have any final questions before we actually solve a problem together? Okay, awesome. So let's go ahead and let's solve a problem. So I've picked out a problem that you guys have not seen before. And so we'll be brainstorming about it together. And hopefully you guys can teach me how to solve it because I don't want to think right now. All right, so this is the problem. It is called cow gymnastics. And I'll send the link in the chat in case anyone wants to follow along. But let's go ahead and read it. And let's go ahead and read it, and maybe we'll be able to figure something out. So I'm actually just going to go ahead and copy this problem statement and paste it into a whiteboard so that we can talk about this while writing stuff down. Okay, cool. So we have the whiteboard. I'll pull up the pen so that we can annotate stuff. Cool. Okay, so to improve their physical fitness, the cows have taken up gymnastics. So Bessie is going to coach the N other cows. When you're reading problems, and I'll sort of talk about this as I read the problem, make sure that you keep track of variable names. When you see a variable name, this should set alarms off in your head because you're like, this is going to be something that determines my runtime. This is also going to be something that determines my runtime. So you have N other cows, and you want to assess their progress as they learn skills. Okay. So you have K practice sessions. Always look at the bounds. K is going to be between 1 and 10. This is really, really small for a computer. Computers run very fast, and 10 is a very, very small number. It only becomes big when you're saying in the thousands or the 10,000s or the 100,000s. When you see something that's double digits, you should always, alarm bells should also go off in your head, and you should say just bash. When you see n is double digit, and particularly in bronze, in other divisions, it might not mean this because it can be a very high polynomial, but when n is double digit, you should always think that you can bash the problem. So we see that n is 10, k is 20. Let's see what this means. So we have k practice sessions. Bessie will rank the cows according to their performance. Okay, so basically, you have k training sessions. So this is training session 1, training session 2, training session 3. And she's going to rank all of the cows. So let's just say that we have cows 1, 2, 3, and 4. So maybe in training session 1, cow 4 was the best cow, cow 1 was next best, cow 2 was next best, and 3 was really trash. They were the worst cow. And then maybe in the training session 2, you had 4, 1, 3, 2, which means that 4 was really good, 1 was less good, 3 meh, and then 2 was really bad. And then 4, 2, 1, 3 is what happened in the training session 3. So basically, every time they train, Bessie will rank them. Okay, let's keep reading. And there's a definition here. These are very important. A pair of two distinct cows is consistent if one cow did better than the other one in every practice session. So looking at this setup here, does anyone want to provide a cow that obviously is consistent with every other cow? It should be very obvious by looking at this. Feel free to unmute or throw your response in the chat. I'd really appreciate it if you guys interacted, which makes this a lot more fun with me, and hopefully it's also more helpful. Yeah, exactly. So cow 4 is obviously going to be consistent with every single other cow, right? Because we said that two cows, I and J, are consistent if one cow is always better than the other one in every practice session. So in fact, 4 is always the best. So it's always going to be consistent with any other cow because it's always going to be better than the other cow. So that's really good. That means that you understood the problem. Cool. So now we understand the premise of the problem, right? And oh, actually we don't, because we don't actually know what we're supposed to find. So the question is, what is the total number of consistent pairs? Okay, so now we understand the problem, right? Basically, for these cows 1, 2, 3, 4, you're going to want to ask the question. You're going to want to see, okay, is cow 1 consistent with 2? Is cow 2 consistent with 3? Is 3 consistent with 4? Is 1 consistent with 3? 2 with 4? 1 with 4? 2? Okay, well, that's it. And then etc. Like, if is 1 better than 2, or is 2 better than 1? Is 2 better than 3, or is 3 better than 2? Etc. 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 And then you simply count the number of ones that are valid, and then you return. Cool. So hopefully this makes sense. Another sort of important thing that we will need to look at when we solve this problem is to look at the input and output format. But don't worry about that too much right now, because right now we need an algorithm. Does anyone have any methods that they think would be a good idea to solve this? Any proposals? Please feel free to unmute. Feel free to type in the chat. What do you think we could do to solve this? And provide a justification for why this is good. or why it's not bad. I'll give everyone maybe 2 minutes to think about this. And just as a hint, which of the techniques that we talked about previously in the class seem like a good starting point for doing this? I said it earlier. It starts with a B. Any takers? Ah, yeah, exactly. It's called bash. And does anyone want to explain how we bash this? And when you explain bash, you need to sort of outline what the solution space is. So obviously we're going to search the entire solution space, but what is the solution space? What are we bashing? Or in other words, when you say bash, then we're going to need to try a lot of different things. What are the things that we are going to try? So here's a hint. What is the maximum possible answer given some n? If you have n cows, what is the maximum number of what is the number of things you have to check to be able to compare to two different things? Or in other words, we said that a pair of two distinct cows is consistent if blah blah blah. How many pairs of distinct cows are there? And yeah, exactly. That's good. There are 6 distinct cows if n equals 3. Can you give me a general formula if we have n cows? Okay. Okay. So I'm not sure if any of you guys have studied this area before, but basically the answer is n choose 2. This is a thing. I'm not sure, maybe this is out of the scope of this course, but basically if you have n cows and you need to check all distinct pairs of cows, then you have n choose 2 different pairs that you need to check. But actually, in this case, our answer that we're looking for is not really n choose 2, because a cow can be, if you look at some pair ij, I can be better than j, or j can be better than I. So actually, we don't want to check n choose 2. We need to check all n squared possible combinations. And I'll explain why this is the case. So let's think about this in terms of like a matrix, right? So if you have cows 1, 2, 3, 4, 5, and you have cows 1, 2, 3, 4, 5. Should probably like scroll. So if you have these 5 cows, if we organize them into this big matrix, right? This is a 5 by 5 matrix. And let's say that this is the better cow and this is the worst cow. So at every matrix, you're going to be asking the question, is this cow on the side that we called better, is it better than the worst cow? And of course, we do not want to compare cows with each other, with themselves. So we're going to X all of these out. Or actually, in fact, when we code this up, we will actually find that it doesn't matter. But anyways, okay, so you have this matrix. if one of the size is n, then obviously you have n squared different things that you have to check. And because they said that n is less than or equal to, I don't quite remember. N is less than or equal to 20. What is 20 squared? That's 400. So n squared is less than or equal to 400, which is actually really, really efficient. A triple digit runtime is very, very fast. So this way you sort of know that you're gonna be fine. And basically what you need to do is you need to check every single cell in this matrix, right? If you're at this cell, you need to check whether cow2 is better than cow1 all the time. If you're at this cell, you need to check whether cow4 is better than cow1 all the time, et cetera, et cetera, et cetera. So, and the nice part about this is that this accounts for both directions. If cow2 is not always better than cow1, it's also possible that cow1 is always better than cow2. But because we've organized this in this big matrix, you're going to be checking all different possibilities. And that's what makes this a good, complete search, or in other words, bash, because you're checking all different possibilities. For every single cow, you need to check whether this cow is better than every single other cow consistently. And if it is, then you add one to the answer. If it's not, you don't. Does this make any sense to everyone? If this makes sense to you, react with a thumbs up. And if it doesn't, react with like a question mark in the chat, because I really want to make sure that this is clear. And this should be clear because we've talked about complete search before. Okay, so I'm not seeing any responses, and I don't really know how to take this. Are people confused, or are people clear on what's going on? Feel free to say confused, because that means that I didn't do a good job of explaining. It's not your fault at all. But if that's the case, then I would like to re-explain it so that we're all on the same page. Okay, I'm still not seeing any responses. Are people following at all? I really need to make sure that this is clear before I move on. Otherwise, none of the rest of this is going to make sense. Like if it doesn't make sense, please let me know. Like please type no. Please don't type nothing. Okay, cool. Interesting. Let's try to re-explain everything. Let us re-explain everything. I think this is very important, and we need to be clear on all of this. Uh-oh. Okay, this whiteboard is glitching. Cool. So, does anyone want to explain to me what a bash is? I feel like this is the most important part. Please unmute, unless, otherwise I will call on you, and I don't want to do that. Because I want to make sure that we're all on the same page. Eric, do you want to explain what a bash is in very abstract terms to summarize? Okay, so he might be AFK. Brandon, do you want to explain what a bash is?
What's a bash?
Do you remember complete search? We might have talked about this before.
You mean bash? No.
Okay, does anyone know what a bash is? Okay, interesting. Cool. No worries. This is perfectly normal. No worries. So let's talk about what a bash is. Complete search. So a complete search is not a command language, and let's call it a bash. So fundamentally, what is a bash? A bash is when you have the following. You have a property that you're looking for, right? You have some property that is going to be present among some certain data points, and you want to figure out which data points contain this property. So what is this property? Currently, a property that we want is that these cows, if you have some cows, cow 1, and you have another cow, cow 2, if you have these cows, cow 1 is always better than cow 2. So how do you check? Well, you go to the first training day. So down here, the first training day, is cow 1 better than cow 2? Yes or no? Thumbs up or thumbs down in the chat. Yes or no? Yes, right? So cow 1 is better than cow 2 on day 1. Is cow 1 better or worse than cow 2 on day 2? It's better, right? But on day 3, it breaks down because cow 2 is better than cow 1. So actually, this property does not hold for cows 1 and 2. But if we look at something like cow 4 and cow 1, it's very trivial to realize that cow 4 is always better than cow 1, right? Because cow 4 is always first place. And if you're always first place, everything else is worse than you. And basically, it'll be good. Like this is a good. So this property holds. So fundamentally, when you're doing a complete search, you're looking for some property. You're looking for some property. And you want to know, so you have some property, you're given some property, and what you were asked for, your task, is to find all examples. So it can take many forms. This is one. So for example, it can be find all examples, or it could be count the number of examples. And there is a very big distinction between these two things. When you count the number of examples, you can often utilize some really tricky insight to actually do the math without finding all the examples. There are a lot of different ways you can do this. Most of it is just combinatorial thinking. But if you're asked to find all the examples explicitly, then you have to specify which ones are the ones that satisfy the property. In this case, when you count, you just have to say how many will satisfy the property. And usually you can deduce this mathematically. But your task is either to find all examples or count the number of examples that satisfy this property, right? And in this case, what was our property? Our property was that some cow I is always better than J. This is the property that we have been looking for. This is the property. So we're given a property, we're tasked with counting the number of examples or finding all of the examples that satisfy the property. Just as a quick concept check, which of these is our problem asking for right now? Are we being asked to find all the examples, or are we being asked to count the number of examples? Exactly, right? We're being asked to count the number of cows. So if you see down here, count the number of consistent pairs. So this is actually a counting problem. So usually in counting problems, you can use some clever trick to avoid having to find all of the examples explicitly. But in this case, because we're in the bronze division and everything is really small sized, we can actually find all the examples explicitly. Usually finding all the examples is more naive and easy to think about than counting, because when you count, usually to speed things up, you need to have some mathematical insight to figure out how you can count more efficiently. But if you can find, then obviously you can count. So finding is actually the sort of the super problem of counting. If you've counted everything, you haven't necessarily found all of them. If you found all of them, you can simply just count the number of things that you found and you have the correct answer. So this is the important distinction. So right now we'll be focusing on finding all the examples. So now becomes the question. When you say find all the examples, you need to account for all different possibilities. You have to account for all the possible things that could be a hit. So This is where the bash comes in. How many possible hits can we have? This is what I was asking earlier. And if you've already answered the question, feel free to answer it again. How many different things do we have to check in order to make sure that we've checked everything? To be sure that we've checked everything, how many things do we have to check? And let's just use a simple example. Let's just say n equals 3. We have 3 cows. How many different things do you have to check if you have 3 cows? So we have an answer that is 6. I don't know if I would agree with that. 3, I'm not sure I would agree with that either. Remember that we're talking about pairs, right? What is an example? So one good way to think about this is when you're trying to find all the examples, you should be asking yourself, what constitutes an example? What makes an example? Does anyone want to explain what makes an example in our case? What are the parameters of an example? Or in other words, what kind of information do you need to figure out whether the property holds? Exactly. So you want to know if a cow always does better than another cow. So what constitutes an example in this case? What information defines an example? I'll just give you guys the answer. It's a pair. So you have a pair of cows. You have a cow I, you have a cow J, and this constitutes an example. The answer is IJ. You need to go through all different pairs of cows and compare them. See if cow I is better than cow J. So given this information, if you have 3 cows, how many ways can you compare these 3 cows with each other? And remember, the direction matters. Cow I better than cow J is not the same thing as cow J better than cow I. So how many ways can we pair them up? So we have an answer, 12. Let's check it. Let's see if you're right. So you have 3 cows. Let's just say you have cow 1, cow 2, cow 3. And let's literally just enumerate all the possible choices, right? You can compare 1 with itself. You can compare 1 with 2, 1 with 3. Cool. You can compare 2 with 1, 2 with 2, 2 with 3. You can compare 3 with 1, 3 with 2, 3 with 3. Are there any other combinations? I don't think so. So this comes out to an answer of 9. And you could have seen that by saying you have 2 slots. In the first slot, you could choose any of the cows to compare. And then in the second slot, you could also choose any of the 3 cows to compare. And 3 times 3 is 9. So 9 is the correct answer. And if you wanted to generalize this, you might notice that 9 is actually just the square of 3. So the general answer would be, we need to check n squared different things. And n squared can be very bad if n is very big. If n is above 1000, it will be too slow to run on your computer. But since n is only double digit, it's only 20, you can actually do n squared very feasibly. So here's the plan. We're going to go through all possible enumerations of the comparisons, and I've actually just written them out here. We're going to compare all possible things, and we're going to check whether I is always better than j. Hopefully that makes sense. That's probably the most simply I can explain it. So now we have a separate question. How do you check whether I is always better than j? Does anyone want to give me some pseudocode or some logic to check this? We're getting really close, so this is really good. But the final piece of the puzzle is, given some I and some j, how do you check whether I is always better than j? Do we need a loop? Do we need some if statements? Do we need both? Does anyone want to explain how we can do this? Yes, exactly. So if a cow's index in the list is always greater than another, or like less than, or it doesn't really matter. So to do this, how would you do this? You would basically put a loop, right? You would go through all of the trading days and check whether the index of one was better than the other. Exactly. That's really good. So this is our solution, right? And so to sort of clarify what our solution should be, let's go ahead and outline our pseudocode. Let's write some pseudocode. Let's do it in red. Pseudocode. Okay, so to check all n squared possibilities, basically we're going to need to do for I equals 0, I is less than or equal to, I is less than n, I plus, okay, this is like C++ syntax, I forgot. For I from 0 to n minus 1, then for j from 0 to n minus 1. If you go inside this for loop, basically what you'll have is you will have oh, I'm very confused. Interesting. Okay. So inside this loop, you will have i's and j's. And so inside here, you're going to have cal I is better than cal j. And it's a question because we don't know. And then so now we check whether I always better. And so if so, answer +1. And then at the very end, you just return the answer. So that's pretty much it. That's all we need to do. That is all there is to it. Cool. Does this make sense? If it doesn't, let me know. If it does, also let me know. All right. Well, it'll become a lot clearer when we actually do the problem, and it'll be a lot easier to reason about once we actually do the problem and I explain all the code. So let's dive into that. All right, so this is our brainstorming. Now we're going to write some code. We're going to be using Replit, which is our trusty online C++ editor. And if you notice, and I'll split this to the side because we need to look at the problem as well. Wait, what? Oh, cool. So this is our editor, and we have the problem here. Basically, we need to create some files in and out so that we can read and output the input. So we should go down here to files, add a file, Maybe like gymnastics.in. Create another file, or we don't actually need to create it because C++ will create it for us. Then we should copy this input in so that it says gymnastics.in. Okay, so we're in our C++ file. I'll explain what I'm doing so that you can sort of gauge, what's going on. So we need to read in the input. And so this is when reading the input format is going to become really important. So you have the first line of the input contains two positive integers, k and n. So we have to define two integers. So this is int means define two numbers for me, dint k and n. And cin, kn basically means please read in the first two numbers in the input, and that's k and n. Cool. So that's going to be it. Next, we need to create a matrix to help store all of this data, right? Because they said that each row is basically one training day. So this is the first training day, second training day, third training day. And so we're going to need some matrix. Let's call it M, and we're going to make it M. It's going to be K by N, because each training day we have K things. So we have K training days, and each training day we have N outputs or N things, like there are N cows that are being rated at every training day. So then to populate it, we need to loop through all the possible values. So I from 0 to K, and then for J from 0 to N. And for every moment, we're going to be reading in a new number. So we're going to be saying the current number is cur, and we're going to read it in. And here's the tricky part. Do we want to store the ratings, the ranking that Farmer or Bessie gave them, or do we want to store the index? In fact, I think it's going to be a lot easier if we store the index. And sort of, let's explain what this means. So currently, we're saying that cow 4 was first, cow 1 was second, cow 2 was third, and cow 3 was fourth. This isn't actually that useful to us. What if we had a representation where we could say, where we could instantly look up which cow, if we had some cow, we could ask, where did the cow rank? And this is going to be far more useful because when we're doing the IJ, scanning over all the possible IJs, we're going to be asking the question, where did cow I rank? Where did cow J rank? And is this rank higher than the other one? So what we'll do is we're not going to simply just do Mij equals cur. This would give us this would mean that J represents the ranking. So 0 means the best one, 1 means the second best one, 2 means the third best one, 4 means the third best one, 3 means the fourth best one. Instead, we should swap these. We should do cur equals J. What this does is it says, it means that for every single cow, the cow at position cur, which is the current cow, this one is the fourth cow, this one is the first cow, this one's the second cow, this one's the third cow. This cow ranked at J on day I. So cow J, so on training day I, cow J ranked, cow cur ranked at J, ranked Jth best. And since C++ is 0 indexed, we need to reduce this by 1 because these cows are 1 indexed. But hopefully this makes sense. We're storing a big matrix where on training day I, you will know that cow at position cur ranked Jth best. And this will be very useful because if we go to this matrix and we're like, what is M0, 0, 3? This is going to tell us on day 0, where, which rank did cow 3 achieve? And this is the direct question that we need to answer when we're checking whether one cow is always better than another. So this is just like a clever trick that you can use to reduce your runtime. Otherwise, you would have had to scan through this entire array to figure out where your cow was. But now we've reduced it to a constant time lookup. All right. So you have this. And now we're going to have, this big matrix. It's going to tell us on day 0, which rank did some certain cow achieve. And now all we have to do is scan through all the possibilities and record the answer. So we're going to initialize a number called answer. And we're going to do another loop, right? We're going to loop through all the possible cows. And we're going to say, now we have a cow I and cow j. Did cow I always do better than cow j? So the way we can check this actually is you know, is to do the following. We initialize a variable called OK, and it's going to be true initially. And what we're going to do is whenever we reach a contradiction, if we ever reach a point where cow j actually did better than cow I, we will set OK to false. And at the very end, we will check the value of this flag. And if it's still OK, then that means at all locations, cow I was better than cow j. If it's false, then we know at least one location, there was one time where cow j did better than cow I. And so if OK is still true by the end, we can add 1 to our answer because we know that it was good. So then we can just loop over all of the days, right? All of the we can loop over all of the all of the training days. And for every training day, we're going to ask, well, at training day K, what was the rank that I achieved? So what rank did I achieve? And so then you go to mkj. So this is what rank did j achieve? And if you have these two values, then you can basically say if mki, if this rank was actually greater than mkj, so what this means is if I actually did worse than j, this is really bad, right? Because this means that I was not consistently better than j, so then we can set OK to false. And then at the very end, if OK is still true, then we're going to add 1 to the answer. This just means +1. And then at the very end, all you have to do is return the answer to print it out. Another thing at the very beginning that I did not do was we need to open the file. So we need to open gymnastics.in. We're going to be reading the file. This goes to standard in. Free open gymnastics.out. We're going to be writing to this file, and we're going to pipe it to standard out. Cool. So this is our entire program. Just to recap, at the very beginning, we wanted to create a matrix that could very quickly tell us on day X, what rank did some certain cow achieve? And this is what we built here. We stored that in a big matrix M. And then we did the bash. This is the complete search, or in other words, the bash, where we tried every single different pair of cows. And we asked, did cow I always do better than cow J? So to do this, we had this nice trick where we said, assume that it's true. And if you ever find any evidence that tells you that it's false, well, then too bad, it's false. But if you don't find any evidence that it's false, then we know that it's true because we looked at everything. So we initialize a flag to true. And every time we ask, okay, so did I actually perform worse at this time? And if it actually did, then obviously it's not okay. A cow I did not always do better than cow J. So we want to set the okay flag to false. And eventually, if everything is still okay by the end, we know that cow I was always better than cow J. So then we can add all the answer. Cool. So let's run this and see if it works. If you hit run, it's going to finish and it's going to spit out a file called gymnastics.out. If you click gymnastics.out, it's going to say 8. And that's not the correct answer. So that's not good. We need to sort of figure out what's going on. So I have actually intentionally done this. Does anyone have any ideas as to what went wrong? This is a little bit of a difficult question, especially because I wrote the code and you didn't. But in the interest of time, I think I'll just tell you all, this is an important thing. You need to be able to reason about your code and pick out bugs or incorrect things that you might have assumed that aren't actually correct. So there's a big problem here. when you loop through all of these possibilities, and this is actually evident in here, there's a big problem. Does anyone spot the problem here in this big area? Does anyone spot a problem? This is the keyword, distinct cows. Does anyone spot a problem with the things that we're checking here? So Amy, you're right that the answer that I got was double the correct answer, but you need to be careful about drawing these kinds of conclusions. Because it's not always, this doesn't always extrapolate. I don't think the problem's that we counted twice. So there's another suggestion, which is that the same cow was repeated twice, and that's exactly correct. We said that a pair of two distinct cows is consistent, but here we're actually checking the same cow against itself, and these are not distinct cows. So we need to put a check in here. We need to say, if I equals j, which means we're comparing the same cow, we just continue, which means skip. This means skip. Skip the current checks if we're looking at the same cow. They need to be distinct. So let's run this again. And lo and behold, we get the correct answer. The correct answer is 4. And we eliminated those issues. So this was just sort of like an attention check. Were you paying attention? Because some of these problems can be quite tricky in that they give you very small details in the problem statement that can completely change the problem. So if you don't read it properly, you will get it wrong. Well, currently we aren't really sure that this solution is correct unless we actually submit it to the server and check. So I think now what you need to do is right click on the main and hit download. Save it somewhere in your computer. Like I'll put it on in my programming folder. It should just be called main.cpp. Then you'll come down to USACO. You'll sign in. You'll select C++. You'll go to main.cpp. You open it and you submit the solution. And hopefully it gives us the right answer. So it's grading. The first two are correct. That's a good sign. And then it turns out all the tests are correct. And we've successfully solved the problem. All right. So hopefully that shed a little bit of light on the problem solving process. I know that some of this might be a little bit confusing. Some of the terminology that I use, for example, the word bash might be a little bit confusing. But fundamentally, if we just review everything we talked about, a bash is when somebody gives you a condition, in very mundane terms, it could be, I want to eat food that will make me go broke. So let's just say I want to eat something that costs less than $10. And this could be a problem that you ask a computer. You're just like, find me a restaurant that costs less than $10 around here. And a complete search is basically to go through all the possible restaurants that you could possibly go to and check whether there are $20. Their food costs less than $10. So fundamentally, strip everything else away. Brute force is when you have a certain property that you're looking for that you don't really know how to find intelligently. So you simply just go to all the possible objects that have this property and check whether they're fulfilled. And that's basically what we did, right? In this problem, we were asked how many pairs of cows are there that fulfill this property? And basically all you had to do was say, well, there aren't that many pairs of cows. So let's just look at all the possible pairs of cows and see how many fulfill this property. And this is a very powerful method, especially in the bronze division, because the constraints on the size of the inputs are pretty small. So you can actually feasibly do this. Now, just to give you a scope, an idea of what's coming ahead, there's a huge amount of information in the world. And often you won't have sizes that are only double digits. You can actually get like 8-figure sizes. Just think about the number of people that use Facebook every day. I'd say millions, hundreds of millions of people definitely log on every single day. They probably have billions of users, registered across the world maybe. And when you write algorithms that work with data that big, you cannot afford to have things like n squared. N squared is actually very bad when you have that kind of data. So the whole point of USACO is to in the bronze division, it's just solving problems. You don't really have to care about time complexity. But when you move on, you will start to care about efficiency. You care about solving problems quickly and efficiently. And so that when you work with real world data, with millions and billions, even trillions of data points, you don't write algorithms that will take hundreds of years to actually run. Like an n squared algorithm applied to trillions of data points will probably take longer than the existence of the universe to run or something if you run it on a classical computer. This may be somewhat wrong, but it's on the correct order of magnitude. So very, very long time to run. But in this case, in bronze, we have double digit sizes. You can run n squared very quickly. As you can see, it ran in 2 milliseconds, which is very, very fast. So yeah. Anyways, I hope this was helpful. Basically, when you read the problem, you should always think, can I, they gave me a property that I'm supposed to be looking for. Can I search for this property over all objects that have this property? Just literally look at everything and check whether they have the property. And if you can, well, then you've solved the problem quite easily. And after we talked about sort of the intuition behind solving this problem, we also implemented it in REPL. I can actually share this. I can share this REPL with all of you in the Zoom chat. So if you want to look at your code, or look at this code after the fact, you can. So yeah, basically, we've gone through the process of preparing for the Computing Olympiad. I have faith in all of you. I feel like you are going to do very well because you've done well in this class. So again, super powerful concept of using MIT App Inventor to solve these kinds of problems, because you don't have to think about the syntax. You don't have to worry about all of this stuff that I wrote here, annoying things like, for loops, what all these different characters mean, why there's semicolons everywhere, why are these angled brackets everywhere. You don't have to remember any of that. You don't have to know what free open is, what IOStream is, what standard in, standard out is, what a namespace is, what an include is, why we return 0 at the end of the main function. All of this you don't care about. All you care about is thinking about how to solve problems. And now that you know MIT App Inventor, you know how to code, you can learn C++, do a heck ton of practice, and then I believe you will do well within the next competition section. And I expect to see many of you in the silver division or beyond very soon. So yeah, that's pretty much all I have for you today. If you have any questions, feel free to leave them in the chat. Otherwise, congratulations on finishing this course. It's really impressive that you guys are doing this at such a young age. So keep your chin up. It's hard stuff, but it's also very rewarding. This stuff is very important in our modern day and age where everything is on computers. Everything is being processed by algorithms. Writing efficient algorithms is incredibly important. So you guys are well on your way to contributing to this movement. Thanks, y'all. Have a good day.
All right, thank you, Kevin. Thank you very much. The presentation was awesome. Thank you. It was not only informational, but also very inspiring. Okay, so yeah, just for our students, some final words for the students. I know USACO by no means by no means an easy kind of like a practice. It's challenging, right? It's essentially the purpose to design it is for challenge smart guys. So you've been doing a great job. Believe me, even though you probably feel like you not yet fully understand every problem, or you have done only a fraction of the problems, that's a great start. You should feel that progress, right? Compare your feeling now and what you felt about like 2 weeks ago. So you should feel much better. I understand if, see here, your target is pretty high. So a lot of times you're gonna feel like you are in the dark for a while. So that's pretty normal. So the thing that the takeaway from Kevin's presentation is, number one, you're gonna review all these problems. You're gonna do it. I mean, you're gonna review what you have already done. You probably gonna do it like multiple times, and extend your practice to more problems. So yeah, you're gonna spend time. Just be persistent. And eventually you're gonna feel like you have something called the instant idea about the solution. So yeah, let's expect that happen, even though you may not have that feeling for now. So again, I want to say congratulations for all students. So you've done a great job, and this is this will conclude this class, and I'll see you for we're gonna stay online for still we're gonna in the group so we can communicate. We still can network each other, and for many of the students, I'll see you next week in the TechBots class. All right, that's all for today, and you all have a great weekend.